All right, this is the second half of Unit 2, Lesson 1. So we're going to pick up on one-sided and two-sided limits. I've also posted a couple other videos in Google Classroom that also give explanations for one-sided and two-sided limits, as well as for the sandwich or squeeze theory. So one-sided and two-sided limits, sometimes the values of a function f tend to be to different limits as x approaches a number c from opposite sides. So when this happens, we call the limit of f as x approaches c from the right hand limit of f at c, and the limit as x approaches c from the left hand limit of f at c. So the notation, there's a little plus sign right by c, and there's a little minus sign for left. So right is positive, basically, and left is the negative, is a minus sign. So in example 7, it says function values approach two numbers. So the greatest integer function f of x equals the integer x has different right hand and left hand limits for each integer, as we can see in figure 2.5. So for example, the limit as x of integer x as x approaches 3 from the right equals 3. Okay, so I'm going right, following the pink arrows. So as we go right, my y value is 3. Okay? And the limit of x approaches 3 from the left, which is the blue arrow, gives me a y value of 2. So the limit of integer x as x approaches an integer n from the right is n, while the limit as it approaches n from the left is n minus 1 in this case. Okay, so I was following the blue arrows for the left and the pink for the right. We sometimes call the limit f of x as x approaches c the two-sided limit of f at c to distinguish it from one-sided right hand and left hand limits of f at c. So theorem 3 shows how these are related. So basically, if the function has a limit of L, that means the function as it approaches c from the right and c from the left also need to be L. Okay? So in order for it to have a two-sided limit, it has to approach the same value from the left and the right side. Okay, so the greatest integer function f of x equals integer x on example 7 does not have a value as x approaches 3. Because if you see, as x approaches 3 from the right, it gives me a value of 3. And as it approaches 3 from the left, it gives me a value of 2. So example 8, explore right-hand and left-handed limits. So all the following statements about the function y equals f of x graphed in 2.6 are true. So at x equals 0, as I approach from the right, so I'm going this way, okay, is 1. My y value is 1. At x equals 1, so I'm going this way, as I'm approaching it from the left, it gives me 0. Okay. Even though f of 1 equals 1, because f of 1 is 1 right here, that's that closed dot. So the limit as x approaches 1 from the right is 1. So the limit as x approaches 1 doesn't actually exist because the right and the left hand limits aren't the same. At x equals 2, so as I approach from the left, it gives me a value of 1. As I approach the limit from the right, it also gives me a value of 1. So the limit x of 2 is 1, even though f of 2 equals 2, because f of 2 is this closed dot up here. Okay? So the function, they have to have a line basically connecting these, either open or closed circles. Okay? At x equals 3, the limit as x approaches 3 from the left is going to give me 2, and as it approaches 3 from the right, it's also 2. So the limit of x as it approaches 3 is 2. Okay? At x approaches 4, there is no limit from the right because there's nothing over here. It's like hanging out. Okay, so there's nothing there. As I approach from the left, it's a value of 1. So the sandwich theorem, it's also called the squeeze theorem. Basically, if I don't know the limit of any particular function, I can take two functions that I do know and squeeze it in between. If their limits are the same, then the one that's in between has the same limit. So in this case, if I look at this picture, this blue line represents f of x. So if g of x, this pink line down here, is less than f of x, which is less than h of x, this top pink line, and they all have, and g and h both have a limit of L and it's the same limit, then that means the one that they've squeezed in between also has that limit of L. So example 9, using the sandwich theorem, I'm going to show that the limit x squared sine 1 of x as x approaches 0 also equals 0. So I picked two functions that have the same limit. In this case, x squared and negative x squared both have the same limit. So as it approaches 0, it's 0. Okay, and this function, this x squared sine 1 of x, is between those two functions. So I'm squeezing it. Since x squared, this top pink, and negative x squared both have a limit of 0 as x approaches 0 of 0, that means this limit, x squared sine 1 of x, 1 over x, also has a limit of 0. So that is the end of Unit 2, Lesson 1.